Okay, we are going to continue chapter number 4, network layer and the data plane. Okay, uh, we are going to discuss topics IP protocol, internet protocol, particularly its uh, header format, how fragmentation uh, is done, and IP version 4 addressing. Okay. Now, as we have discussed in chapter number 4 up to now, we have discussed an overview of network layer, its data plane and control plane, what is its functionality, and what is the architecture of a router. Okay, so now we are going to discuss these topics. As we know that the network layer, what is its functionality? Its first functionality is forwarding. That is, when a packet is arrived, the packet header is examined. That what is, for example, what is the destination IP address in the packet. Okay, so for example, it is the IPA. So IPA address will be searched in the forwarding table. Okay, if there is found an entry, for example, IPA address should be forwarded to the port number 2. So according to this entry, the packet will be forwarded to port number 2. This is called forwarding. Okay, so this is the first functionality of a network layer, and this is called data plane. Okay, the second functionality is that who builds up this forwarding table. So at the moment we are discussing the per router architecture. So this forwarding table is constructed by a routing protocol. For example, we have different types of routing protocol: RIP, OSPF, BGP. This is called control plane. Okay, so these protocol are used. One of these protocol is used to construct or to develop this forwarding table. Okay, as we have discussed that at each layer we have some protocols. For example, at the application layer we have discussed DNS, HTTP, etc. So similarly at transport layer we have TCP and UDP. These are the protocol that are used in practice. So in the network layer we have only one protocol, and that is IP protocol. Okay, so we will discuss its addresses format and its header format. Okay, so along with this, there is also a supplementary topic that is called ICMP, and this ICMP protocol, though it is application layer protocol, but it is used to report the error reports for error reporting of network layer. So that's why we will discuss it in the this chapter. Okay. Now we are going to discuss the IP datagram format. So in IP header, the first field, it is called version. You can see that in IP we have header lines: first header line, second header line, third header line, fourth header line, and fifth. These 5 header lines, they are mandatory. Okay, and these header lines, they are optionals. They are optional. Okay, so in the first header line, each header line is 32 bits, 4 byte. So in the first header line, we have first field that is called version. This version, it represents the protocol version. Okay, so currently we have two types of protocol version. One is IP version 4 and one is IP version 6. So this is basically the version number. It is represented here in this field. Okay, the second field, it is called header length. As we have discussed that in IP protocol, in IP headers, these fields are optional. These fields are optional. So therefore we have header length, that how much is the header length, is this header. So it is basically represent the header length, the size of the header, IP header. Okay, and the third is type of service. This field is basically used for different purposes. Okay, so this field is used for different purposes. So let me explain two examples in the next slide. Type of service. Basically, if you do remember, so we have discussed explicit congestion notification. If you do remember that when a source nodes transmit the packet, okay, so the ACN field is set to 0, that there is no congestion. Okay, and when this packet is passed through a router, okay, through a router, so the ACN field, it is used in the type of service field. 2 bits in the IP header type of service field, it is marked by network router to indicate congestion. This ACN field, it is present in the type of service. Okay, in the type of service, this is ACN fields, these 2 bits are present. So this shows that ACN field is 0. But when this packet is passing through the router, this router, and there is congestion, then this router will make this field 1. This field will be set to 1, for example this one. Okay, and then the packet is forwarded further. Okay, so this type of service field, they are used, so they will be forwarded further. Okay, so when the packet is received here and with the ACN bit is 11, so this destination will send feedback or data to the source, so it will set ECE bit to 1 in the TCP header. So this means that the source will come to know, the source TCP will come to know that the congestion is happening. So I'm going to explain that the type of service field in the IP header, so it has 2 bits and they can be represent the ECN, explicit congestion notification. Okay, so this ECN field is set to 11 when a router forwards the packet and the router feels that the congestion is going to happen. Okay, so type of service field is used for this purpose as well. Okay, so this is one example, this is one use of type of service field in the IP header. Next, as we have discussed that when the packets are arrived, they are classified into different classes. For example, these packets, they have higher priority, these packets, they have lower priority, and these packets, they have lowest priority. So when the links become free and the node want to transmit the packet, so the packets are transmitted according to scheduling. Okay, so the according to which scheduling algorithm are used. For example, if we want to transmit the higher the round robin means that the first packet from the highest priority queue will be transmitted, then from lower, then from lowest, and then going back to the highest priority queue. So these types of classes for the packet, they should be identified by using the type of service field. So the type of service field, it can be used to set the priority, that whether the packet belongs to highest priority or packet belongs to lower priority or packet belongs to lowest priority. Okay, so these are the 2 applications that I have discussed with you for type of service. So we have discussed the version field, the header length, and type of service. And next is the length. Okay, so length, it basically represents the length of total packet including header plus data, header plus data. So if the header length, it represents only the header length, and the length field, it represents the header length plus data. So if we can minus length from header length, then we can get what? The data length. Okay, so we have discussed version number, header length, and type of service. Now we are going to discuss another field, and that is called time to leave. We are going to discuss another field that is called time to leave. This is an integer value. Okay, and it is basically decremented when a router receives the packet and the router forwards that packet, then before forwarding, this field is decremented by 1. Okay, so let me explain it through an example. The TTL field, suppose that we have a source. This is the source machine, and it wants to transmit a packet from source to destination. Okay, now suppose this field, it has the TTL equal to 3. The TTL value is set to 3. So this is basically shows what, so time to leave, this is set 3. When this packet is received by the first router, so the router, after receiving this packet, the router will forward it to the best path according to forwarding table. Okay, so before forwarding, when this TTL will be decremented, this TTL will be decremented like this way. When this packet is received by this router, so it is forwarded, but before forwarding, the TTL value is decremented, so it will become 2. Similarly, when this router forwards the packet, so this will also decrement the value TTL equal to by 1. You can see that the TTL value is decremented by 1, so it will become 1. Okay, when this packet is forwarded by this router, when it is received by this router, and when it forwards, it will also decrement the TTL, it becomes 0. So whenever a router finds that the TTL become less than 1, 0 or less than 0, then the packet is discarded. Because its time to live, this time to live, it is expired. So the TTL value is used. Why? It basically defines the liveness of the packet in the network. Okay, because if a node transmit a packet and its destination is not present in the network, so it will move between the it will move on. Okay, so if we have a loop, so the packet will be moving on continuously. So to avoid this continuous movement of the packet, so we use TTL. TTL means it basically defines the time of the packet. Okay, but this is not defined in terms of hours or in terms of seconds. It is an integer value. So it represents when the TTL is equal to 3, so it means that the packet should be forwarded up to 3 routers. Okay, up to 3 routers. Up to 3 routers. So when the packet is forwarded up to 3 routers by 3 routers and the packet doesn't reach to the destination, then the packet will be discarded. Okay, so the TTL value, it basically shows the time to live of the packet, but it's an integer value. Okay, and it is decremented by each router, so it doesn't show the time to live, it doesn't show the time to live in hours or in seconds, but it shows that this packet should be forwarded up to how many routers. Okay, so therefore when the source wants to send a packet from source to destination, so the TTL value is set so that the packet is reached safely to the destination. For example, if the TTL value here is set to 3, then it will be discarded by this router. So this packet will never reach to destination. So what should be the TTL value in this case? So the TTL value should be at least more than 5, like 7, 8, 9. So if it is 7, then it will be decremented by this, it will become 6. When it is decremented by this router, it will become 5. When it is decremented by this, it will become 4. Then it will be forwarded here. Then when it is forwarded, it will become 3. So it will reach safely to the destination. Okay, so the TTL value, it basically shows the time to live, but it doesn't show the time to live in second. It shows the time to live that this packet should be forwarded by how many routers. After this, the packet should be discarded if it doesn't reach to the destination. Okay, so we have discussed the version, header length, type of service, and time to live. Now next we are going to discuss another field that is called upper layer. Okay, why so what is its function? So let's see it. So before this, we have already discussed the length field. That the length field, it represents the total length of the packet, including the header and the data packet. And the header length, it only represents the header length. So length minus header length, it represents the data length. It represents the data length. Okay, and it is also represented in bytes. It is also represented in bytes. Okay. So we are going to discuss these fields: identifier, flag, and fragment offset. So through an example. Okay. Basically, 6-bit identifier, why it is used, as we have discussed sequence number in the TCP protocol. Okay, so what does sequence number means? When a sender transmit a packet, so it basically attach a sequence number 1 2 3 4 5 6. So here the identifier is used. Why? When the when the IP packet is originated by a source machine, so it attach an identifier, for example 5, to the first packet. So the next packet, when the when, for example, if I look at here, for example, this is the source machine. It originate an IP packet, so it will assign an identifier, for example 5, to the first packet. When this machine send another packet, so it will have another the next identifier, it will be 6, 7, 8, up to going on. Okay, so the identifier, in for each source they have different identifier. For example, if this source is forwarding a packet, so it will have identifier, for example 6, 7, 8. Okay, so here if the packet is forwarded, it has 6 as an identifier, and here the packet has a 6 identifier. So how to differentiate that this packet belongs to different machine? So basically we use source IP address. So the source IP address of this will be different from the source IP address of this packet. Okay, so basically identifier is used. Why? Whenever a machine, it originate an IP packet, originate from where the packet is originated, from where the packet is started, IP packet is started, so that machine assign an identifier to the packet. Okay, so the identifier is used, and the fragmentation, the flag, it has either value 0 or 1. So if the flag is 0, it means that the packet is not fragmented, or the packet is last one. If flag is 1, it means that this packet is fragmented and it is part of a big packet. Okay, so we will discuss it. Now we are going to discuss the another important field. This is called upper layer. Okay, upper layer field. What is its use? As you know that when a source machine, whenever a receiver, a destination machine, it receives the packet. So the packet are processed first by physical layer, through physical layer. Then the packet is processed through data link layer. Then the packet is processed through network layer. So the network layer, it will examine the destination IP address in the packet. If the destination IP address in the packet, it matches to the destination IP address of this machine, it means that this packet belongs to this machine. So this packet is for this machine. Okay, when the packet is for this machine, then the network layer, it remove the header of IP, and the packet is passed to the next upper layer. So in the upper layer, it is the transport layer, but in transport layer we have TCP or UDP. So whether the packet should be forwarded to the TCP or it should be delivered to the UDP. So basically this upper layer is used. So if it has the value TCP, then the packet will be given to the TCP, not to the UDP. And if this has UDP, then the packet will be forwarded to the UDP. So basically this upper layer field, it contains either TCP or UDP, and it is basically used by the receiver machine, that when the packet is to be delivered to the transport layer, so at that transport layer we have different option. So to which transport protocol the packet should be given. So this packet is used for this purpose. Upper layer field is used for this purpose. Okay. So let's discuss it, the IP fragmentation and reassembly. Okay, now suppose this machine, it wants to send data. Okay, so what is the functionality of network layer? What is the functionality of network layer? So the first of all, the network layer, it has to compute the best route. Okay, for example, this packet is to be moved from source machine to destination machine. So the network layer has to compute the route that this packet will be forwarded along this path. Okay, after this, the packet is now moved from this link, from this source to first router. So they are connected through a data link layer. This is the data link layer. So the network layer, it identifies that the packet should be moved first from this machine to this router. This is called next hop. Now this machine is connected to this router through a data link, and the data link, it can be have different capacity. For example, it is UTP cable, it is coaxial cable, it is fiber optic, it is a wireless link, and so on, so on. Okay, so each link, each type of link, it has a MTU, maximum transfer size. That in each link it has an MTU. MTU means that a link can send how long a packet, that what should be the maximum size of packet for a link. So each link has different type of packet size it can transmit. Okay, so each link has MTU. What does mean MTU means? That each link can send a packet of certain size, maximum size. This is called MTU. Okay, so suppose this link that connects the source machine to router, it can sense a packet up to 4000 bytes. This is the maximum MTU of this link. So this host will make a packet of 4000 bytes. Okay, and now this packet is transmitted from this machine to this router. Okay, now when this packet is received by this router, so it has forwarding table, and forwarding table means that this packet should be forwarded to this router. And now when the packet should be forwarded to this router, so this link is examined, that what is its maximum MTU. MTU means that how much what is the maximum size of the packet for this link. Suppose it is also can send the data up to 4000 byte in a packet. So this packet is already 4000 bytes, so it will be transmitted as it is, because it can be transmitted. Why? Because this link can accommodate this packet size up to 4000 bytes, so it is transmitted. When this packet is received by this router, so this router sees that okay, this packet should be forwarded on this link, but this link, it can have the packet size up to 1500 byte, up to 1500 byte. So this packet that is arrived, it is 4000 bytes. So this 4000 byte, it is more than 1500, so it cannot be sent on this link. Why? Because this link can accommodate up to 500 bytes. For example, if a bottle if a bottle, it has the capacity of 2 liter, and you want to put more than 2 liter, 4 liter, it can be accommodated? No, it cannot be accommodated. So similarly, it cannot be accommodated in this. So what does the IP layer do in this case? So basically, this packet that is 4000 byte, it is more than the maximum size of the packet for this link. So this packet will be divided into number of packets. This is called fragmentation. This packet will be fragmented into number of packets. So the large IP datagram, when it is arrived within the network, within net, so for example, this is a 4000 byte datagram packet, and this link, it can send the packet up to size 1500 bytes maximum for 1500. So 4000 byte cannot be accommodated in 1500 bytes. So this 4000 byte, this packet will be divided into 1500 bytes packets, into fragments. So this is called the large IP datagram is divided into fragment. So one datagram becomes several datagrams. So this datagram, it will become many datagram of 1500 bytes. Okay, Now suppose that we divide this packet into, so what should be the uh, you can see that this packet is 4000 byte, so it can be divided into three packets. Okay, 1500 and 1500, it becomes 3000 and 1500. This will not be 1500, but it will be less than 1500. Okay, because 3000 is accommodated here. Okay, so fragmentation is what we receive in this, and this router we get a packet of large size and it to be forwarded to this router, and this link cannot accommodate the packet up to 4000, but it can accommodate up to 1500 bytes. So this large packet, it is divided into three small datagram. Okay, now when these small packets, they will be transmitted. Okay, so they are transmitted and they are received. So you can see that when these packets are received by this router, and this router can now send, suppose, the packet up to 4000 bytes. So should this router assemble this packet? No, it should not assemble. Okay, because it may happen that we are using packet switching technology. It may happen that some packets are going through this link. Okay, for reassembling, it has to wait that it should receive all the packets, but maybe some packets are moving through this link, so it may not receive all the segments of the packet, all the fragments of the packet. So that's why in IP we have the reassemble, that when the packet is divided, so that these divided packets should not be assembled in every router, but they should be assembled when they are received at the destination, final destination host. When they are received, then the network layer will reassemble these packet into one packet. Okay, and how does it knows that these packets are segmented or not? Okay, so when a packet, so the IP header bits are used. Which IP header bits are used? For example, this packet is transmitted, so it will have length, that this is a 4000 bytes length. It includes the header length plus data packet. It includes the IP header plus data packet. It is 4000 bytes. It will includes this ID. ID means identifier. When the packet is originated from here, so it will have identifier. For example, it has identifier 9. So this identifier 9 will be present in the packet till it reaches to destination. Okay, and these field identifier and fragment flag. So when this packet is transmitted from here and it is not fragmented, it is not divided, so its flag will be 0. When this packet is forwarded from here, it is not divided, so its flag will be 0. And since the here it divides the packet, so the fragment offset will be 1 for the first packet. For the second packet, it will be 1. For the last packet, it will be 0. So we will discuss it, how these bits are set. Okay, so you can see that the identifier field 9, it will be set in every field, it will be 9. So when the packet are received and it has flag, fragmentation flag 1, so it means that packet is divided. It is divided. So it is a fragment of a large packet. So the fragment flag, it basically authenticates to the destination machine when it is received at the destination machine at the network layer. So when the packet has a fragment flag 1, so it means that this packet is divided. So it will wait. It will wait that some other packets, other fragments of this packet will be received, then they will be assembled. So we will show that how this assembling is performed and how this fragmentation is performed. Okay, but till now you should know that why we have IP fragmentation. So each link, it has a maximum MTU, maximum transfer size, that how that each link type, it can have a maximum packet size. Okay, so when a datagram arrives at a router and the packet size is larger than the outgoing link, then the packet will be divided according to the packet size of the outgoing link. Okay, and which and it will be assembled only when it is received at the destination. And how this fragmentation and reassembling is is performed. So this fragmentation and reassembling is performed by using the field, this one, identifier, fragment flag, and offset flag. And how these values are set and how their values are used, let's explain it through an example. Okay, so the reassembling will be only happen at the destination machine, not somewhere else. Okay, now we are going to continue that how a packet is divided. Okay, so for example, when this packet is received, this is the packet, large packet, its size is 4000, its identifier is 9, and we want to divide this packet into the packets of maximum size 1500 bytes. Okay, so you can see that in, as we have discussed, that we have received 4000 byte datagram. So in a packet we have data and header. You can see that as we have discussed it. In a packet we have header, this is the header, and this is the data. Okay, and in the header we have length. Length represents the whole length of the packet. Header plus data, header plus length, it represents the length of the total packet, including header plus data. Okay, so that's why when the packet of size 4000, for example, we have packet of 4000 bytes. Okay, suppose in this packet, as we have discussed, that in IP header, these 5 header fields, first header line, second header line, third header line, fourth and fifth, these are mandatory, so they must be present in each and every IP packet. And each header line is 4 byte, 32 bits, 4 byte. So 5 into 4, 20 byte is the header, suppose. Okay, now suppose that if a packet is received of 4000 byte, so it means that 20 byte is the header, and how much is the data? 3980. 3980 bytes it contains, it is the data, and 20 byte is the header. Okay, now we want to divide this 4000 byte packets into MTU of 1500 bytes. Okay, why? Because this packet is arrived, it is 4000 byte, and this packet should be forwarded to this and this link, and this link can accommodate the packet size up to 1500 bytes. So this 4000 bytes, it should be divided into smaller packets. Okay, so if we have 1500 bytes of packet, then in this 20 byte will be header, so remaining 1480 will be data bytes. 1480 will be data bytes. So you can see that actually we have to divide this data, 3980 bytes, it should be divided such that each packet is up to maximum 14080 bytes. Okay, so you can see that when 3980, so how many packets, when this data is divided into 1480 bytes packet, then how many packet will become? For example, this is a packet of 3980 bytes, and we want to divide this data into packets that can accommodate 1480 bytes. So 3980 divided by 1480, it will become 2.68. It means that we will have 3 packets. One first packet will be up to 1480 bytes, second packet will be 1480 bytes, and the third packet, it is not full 1480 bytes, so it will have less than 1480 byte. Okay, so let me explain it. So you can see that this packet, it should be divided into 3 packets. Why? When the packet it is received, it is 3980 bytes, it contain data, and it should be divided such that a packet size is maximum 1480 bytes data. So this divided by this, it becomes 2 point something. So it means that it will have 3 packets. Okay, 1 packet, 2 packet, 3 packet. Okay. Now, so this shows that when a packet is arrived, so into how many packets this, uh, so when a packet is arrived, for example here, when packet of this packet is arrived, it is 4000 bytes, and this link it can accommodate up to 1500 bytes. So into this packet should be divided into how many packets? So we explain it that first you have to compute what? First you have to compute the data bytes in the large packet that is arrived packet in, and the data bytes of the packets that of the outgoing packet. Okay, so it should be divided, then it will give you that how many number of packets are smaller packets are required. Okay, so it means that this packet it will be divided into 3 packets. Okay, by using this formula. Now the first packet it will contain 1480 bytes data and 20 byte will be header, so it becomes 15,000 bytes, 1500 bytes. Okay, so you can see that from this data, first 1480 bytes they are kept in this packet. They are kept in this packet. So 1480 byte it is the data, and 20 byte is the IP header. Okay, so it becomes total length of the packet becomes 1500 byte. So from 3980 bytes data, 1480 are kept here. So how many are remaining? So 3980 minus 1480, it becomes 2500. Now 2500 bytes of data will be distributed in these 2 packets. Okay. Now in the second packet, now in the first packet, when 1480 bytes of data is kept here, so now we have from 3980 bytes, now we have 2500 bytes data. So 1480 bytes data are kept here in this packet, so its length will become 1500 bytes. Why? 1480 bytes is the data and 20 byte is the IP header. So now we have from here we have 2500 bytes of data. So 1480 will be subtracted from 2500, so now we have 1020 bytes of data remaining. So this 1020 bytes data will be kept here in third packet. Okay, so 1020 bytes of data and 20 byte is the header length. 20 byte is the header length, so its length will become 10,040. You can see that the first packet is a full size 1500 byte, the second packet is full size of 1500 byte, and the third packet is not of the full size, it is of the 1040. So you can see that when a large packet is arrived, so first we have to compute the data bytes, that how much is the data size, and for MTU we have to compute how much is the data bytes. So we have to divide the packet in the larger packet size divided by smaller packet size, so it will give you that how many should be the smaller packets. So you can see that here it should be 3. Okay, so the first packet, second and third, the first and second they are full size 1500 bytes. Okay, in 1500 bytes 1480 is the data and 20 byte is the header length. 20 byte is the header length and 1480 is the data size, and here 1020 is the data length and 20 byte is the header. Okay, so this will really performed. So we have discussed that how this length is specified. Okay, how a large packet is divided into smaller packets, and then how the length is specified. Okay, now in this packet we have identifier 9. and this packet is divided into 3 packets. So in these all 3 packets, the identifier will be 9. The identifier will be 9. Okay, so the identifier in 9 is set in all 3 packets, because these 3 packets, it has that why these 3 packets have identifier 9, because they are divided, they are part of a large packet, and that large packet has identifier 9, and this identifier, it is set by the node that originated this packet. In this case, the source machine that originated the packet, so it has identifier 9. Okay, so it will not change. Now comes that how this fragment offset flag is set. Okay, so in the first packet, the fragment flag will be 1. This means that this packet is divided. This fragment flag will be in the 1 in the second packet, and in the last packet it will be 0. So it means that when the fragment flag is 0 and the offset is other than 0, you can see that when fragment flag is 0 and offset is 0, so it means that this is the last packet, but this packet is not divided. This packet is not divided. When the fragment flag is received 0, so this is the last packet of a fragment, and when the offset is 370, so it means that it has some packets before, so it is not the so this packet is divided. This is part of a large packet. Okay, now we are going to set that how this offset address is set. So we have discussed that when a packet is, how the packet is divided into smaller packets, we have discussed. Then we have discussed that this identifier flag of the large packet, it should be replicated in each and every smaller packet. Okay, same. And we have discussed fragment flag. In the first packet, the fragment flag will be 1, in the second 1, in the third 1, up to, in the last packet the fragment flag should be 0. Okay, and now we are going to discuss how the offset is computed. Okay, so this is done. The length identifier and fragment flag, they are discussed. Now we are going to discuss the how offset value is computed. How this offset value is computed. Okay, when the packet is not divided, then the offset flag will be 0. Okay, now let us discuss, as we know that we have received the data 3980 bytes. Out of 3980 bytes, first 1480 bytes data are kept in this packet. Okay, so its offset is 0, because it is the data from first byte. From the first byte it's 0, so it from the first byte it is 0. Okay, so this offset will be 0. But how long it contains the data? Okay, basically what we do, we divide this 1480 bytes by 8. 14,000, this 1400, because it contains this, it contains the data starting from 0. But how long it contains? So 1480 is divided by 8, so it becomes what? It becomes 185. So basically it becomes 185. So it means that this fragment, it contains the data from 0 up to 184. From 0 184. You can see that this packet, it contains 1480 bytes of data. So 1480 is divided by 8, it becomes 185. So here the data is stored from 0 up to 184 offset, from 0 offset up to 184. And the next packet, it is stored the packet from 185 offset. It will have the data starting with the offset 185. Okay, and how long? You can see that this packet also contains 1480 byte data. So 1480 divided by 8, it becomes 185. So it contains from 185 plus 184, 184, it becomes 369. So it contains the data starting from offset 185 to 369. This first packet, it contains the data starting from 0 offset till how much? 1480 divided by 80. So it becomes 185 offset. Since the offset is started from 0, so it contains from 0 up to 184. Okay, and this packet, it contains the data starting from the offset 185. And how long? So 1480 is the data size in this packet. So 1880 should be divided by 8, it becomes 185. 185 because it starts from offset from 0, so it will be 184. So 184 plus 185, 369. Okay, similarly, so it becomes the data, it has the data starting from offset 185 till offset 369. Okay, and this packet, it contains the data starting from 370 offset. And how long? So you can see that when 1020 it is divided by 8, so it will become something about 118 about. Okay, so you can see that 118 128 something, so it will be so this offset, so this packet, it contains the data starting from the offset 370 to 490 offset. Okay, so we basically in offset we put the starting offset value, okay. So now we have discussed that when how a packet is divided into multiple packets and how the length is set, okay, by using this formula, and how the identifier is set, it is replicated from the larger packet, and how fragment of flag is set, and how the offset value is computed. Okay, now when these packets are received, so you can see that when if this packet is received, okay, so this is fragment flag 0, it is not fragmented, it is last packet. But from offset 370, it means that this flag is fragmented, because if it is not fragmented, then its offset should be 0. It has offset 370, so it has the data from starting from offset 370. Okay, so when these packets are received, so they are how they are added. Basically, this offset flag is used. Offset 0 means that this is the first packet, so it will be stored. And how long it contains? So basically, from the packet length, it will compute the data, and from data it will compute the data length is divided by 8, so it contains the data from 0 to 184. Okay, it contains the data from 0 to 184, so this packet will be kept first. Now this packet contains 185, so from 184 the next is 185, so these two packets are consecutive up to 369. Okay, how it is 369? Because the length is 1500 byte, in 1500 byte 480 is the data, so 1480 is divided by 8, it becomes 185. So it starts from 0, so it will be 184, so 185 plus 184, it becomes 369. So it contains the data from 185 to 369. So this is the first packet, and this is the second packet, and this is the third packet. And since it is 0, so it means that this packet is last. This packet is not the last one. This packet is not last one. So only these packets are received, then they will be, so they will be assembled, but the receiver has to wait till the last packet is received. If the receiver machine, if any of these packet is missing, then the whole packet will be discarded. The whole packet will be discarded because it is not received correctly. Okay, so you can see that from the that how this feed ID, fragment offset, and length is used when the large packet is divided into smaller, and when this smaller packet are received, so by using this fragment offset identifier means that all these packets belong to same packet. So from this offset value, these packets are stored. That this is the first packet, this is the second packet, this is the third packet. from the offset and the length of the size of the packet. It can compute that this is the first packet, this is the second, this is the third. Okay, so this is performed how this is the procedure for IP fragmentation and reassembly in the IP packet. Okay, so now we are going to discuss some more fields. Okay, upper layer is discussed, total length is discussed, fragmentation, identifier, flag and fragment offset, they are discussed. Now some fields are option. You can see these fields are options. Option means that whether you want to include or whether you don't want to include, and it can include timestamp. Timestamp means when the packet is generated from a source, so what was the time, for example it was 10 o'clock. Okay, and it can also contain the record route when the packet is forwarded by each router, so each router can keep its own IP address. So when it is received at the destination, so the destination comes to know that this packet is forwarded by which router, okay, etc. And you can see that we have a header checksum. Header checksum, why it is used? Okay, so it is used, basically it has the same functionality as we have discussed in UDP and TCP. So it is used for bit error. It is used for bit error. And you can see that these header line, they are must. The TCP and the header is basically overhead. The header is overhead because these are extra data. These are extra bytes. Okay, so in the TCP the header length was minimum 20 bytes, and the IP also the minimum, these 5 header lines, first header line, second header line, third header line, fourth and fifth, these header line, they are mandatory. So 20 bytes of IP packet. So 20 bytes is the header for IP packet. Okay, so if we have received a packet which contains the IP header and TCP, so it means that it contains 40 bytes of header. So if you are sending only 1 byte of application data and it contains 40 bytes of header, so header is more than the data size. Okay, so it should not be transmitted. So that's why we have discussed that when a packet of some size, when the data becomes of some size, then the data is transmitted. Okay, so we have discussed it. Okay, now we will discuss IP version 4 addresses in the next class. Okay.